Welcome to qnawire.
Hi everyone, so what we have is a vertical piston cylinder insulated system with a spring that is attached to the cylinder, and there is a supply valve that is attached to the bottom of this cylinder system. The initial volume is 0.11 cubic meters, and air inside this piston is at a pressure of 150 kPa and 22 degrees C. The supply line is at a pressure of 700 kPa and 22 degrees C. We know the final pressure is 600 kPa and the final volume is 2 times the initial volume. What we're asked to find is the mass of air that is entered and the final temperature of this system. So the first thing we're going to do is go ahead and write down our assumptions. Because quantities are changing over time, this is not a steady state process, and we're also going to assume that any changes in kinetic energy, potential energy, and heat are equal to 0. Next, what we're also going to do is assume that the spring that is mentioned in the problem statement is a linear spring. And we're also going to assume that air is acting as an ideal gas. So next, we can write down the pertinent properties. We can say that the gas constant of air is equal to 0.287 kilojoules per kilogram Kelvin. Next, we can also write down our specific heats of air. So we can say that CV is equal to 0.718 kilojoules per kilogram Kelvin. Say that CP is equal to 1.005 kilojoules per kilogram Kelvin. And we can also write down the approximations that U is equal to CV times T, our specific internal energy, and our specific enthalpy can be approximated as CP times T. So next, what we're going to do is take the cylinder as our system, and we're going to do a mass balance. So we can say that the mass coming in minus the mass leaving is equal to the total change in mass of the system. Now, we don't have any mass that's leaving, all we have is mass that's entering. So that's going to be simplified down into Mi is equal to M2 minus M1. Next, we can do an energy balance and say that the energy coming in minus the energy leaving is equal to the total change in energy of the system. Now, I've written this in terms of rates, but we can just go and take these as absolute quantities as well. So we can just say this is E in minus E out is equal to the change in energy of the system. Now we can break this out into its constituents and say that the mass coming in, energy coming in, will be due to the supply line, MIHI. That's going to be equal to our boundary work, WB, plus the change in energy. So M2U2 minus M1U1. Now what we can do is we can insert our mass balance in here as well and rearrange some terms to say that M2 minus M1 HI is equal to work plus M2U2 minus M1U1, and we can use the definition of enthalpy being equal to CV times CP times T and say this, that M2 minus M1 CP times T I is equal to work plus M2 CV T2 minus M1 CV T1. Now what we can do is solve for the initial and final masses in our tank. We can use the ideal gas law to say that M1 is equal to P1V1 all over RT1, and this gives us an initial mass of 0.1949 kilograms. Using the ideal gas law again, we can find the final mass to say that M2 is equal to P2V2 over RT2, and this gives us a final mass equal to 459.9 all over T2. Recall that we are asked to solve for the final temperature, so we have our final mass in terms of the final temperature. So from the mass balance, what this allows us to do is we say that Mi is equal to M2 minus M1, which is going to be equal to 459.9 all over T2 minus 0.1949. Now, since the spring is a linear spring, we can also calculate the boundary work by saying that the boundary work is equal to P1 plus P2 all over 2 times V2 minus V1. And by plugging in these quantities, we see that the boundary work is equal to 41.25 kilojoules. Now, plugging this value into our energy balance, we get an expression that in which the only unknown value is T2. So what we can do is we can say that negative 41.25 is equal to minus 459.9 all over T2 minus 0.1949 times 1.005 times 295 plus 459.9 all over T2 0.718 times T2 minus 0.1949 0.718 times 295. And as you can see, the only unknown value here is T2, so we can go ahead and solve for T2, and we get a final temperature that's equal to 351 Kelvin. Now, using this value, we can actually go ahead and directly also solve for the final mass, because our final mass was equal to 459.9 all over T2, and this gives us a final mass equal to 1.309 kilograms. Now, using our mass relation, we can say that the mass that entered was equal to M2 minus M1, and this gives us a mass that entered as equal to 1.11 kilograms, and that's our final answer.